My name is Francesco Longo. I'm from University of Calabria, and this is a session that is connected to an ongoing research project called So4Sims. So let me share for some minutes my screen. Okay, so this session is a session for presenting some preliminary results of the So4Sims project, that is Smart Operators 4.0 based on simulation for industry and manufacturing system. So this is the outline of this session. We will have very quick presentation from the partners of this project. I will make an introduction for some minutes, and then there will be presentation from Polytechnic of Bari, University of Salento, University of Palermo, University of Basilicata, University of Salerno, and finally University of Calabria. These are all the partners of this ongoing research project. And then we will leave 20 minutes at the end of the session, starting from 5:10 until 5:30 p.m. for question and answer, and as well as open discussion. As I was mentioning, So4Sims is Smart Operators 4.0 based on simulation for industry and manufacturing system. The idea of this project, this project has been financed and supported by the Italian Ministry of University last year in September. So the project was started in September 2019. So we are now just after 1 year of project. The idea is to conceptualize as well as to implement both a methodological and technological framework to practically implement the concept of smart operators in the Industry 4.0 domain. As I was mentioning, the project involves 6 Italian universities. All the universities are located in the south part of Italy: University of Calabria, Polytechnic of Bari, Basilicata, Palermo, Salento, and Salerno. So today we are going to give you an overview about the preliminary results that we have reached after 1 year of project. The idea, as I was mentioning, is to create this framework that will be both methodological. There will be new methodologies that will be developed to support the implementation of smart operators, as well as a technological framework. So our aim is not only to, to collect data thanks to an ad hoc, let me say, digital twin, collecting data that could be useful for the smart operators, but also to set new models that will consider in a synergic way the different aspects of the including as well staging problem and interaction between the operators and other technologies that are part of the shop floor environment. But above all, the idea is then to, to integrate all these methodologies and data coming from the real system in a synthetic, virtual, and simulated environment where we can practically implement the concept of smart operator, and where we can also provide functionalities to real operators that are working in real manufacturing system. As you know, if you feel to the operator 4.0 or to the concept of smart operators, you surely know that you need a number of capabilities. You need sensorial capabilities, you need interaction capabilities, you need physical capabilities, and you need cognitive capabilities. Therefore, it is at the beginning of the project we have also investigated which kind of data we have to collect to implement our concept of smart operators, as well as we have focused our research effort in order to identify possible case study related to different sectors of manufacturing system. Could be maintenance, production planning and control, quality, and so on. But the idea in terms of methodology is to focus on three different areas, let me say: ergonomics and safety of the operators, operator staging problem, and cognitive and learning aspect of the interaction of the operator with the working environment. Therefore, in the next presentation that you are going to see from all the research units of this project, you will see how we have started to tackle all of these different aspects. And Obviously, we have also starting to work to create the final, let's say, environment, technological environment, where we can carry out a comprehensive set of verification and validation of the models that we are going to develop in the next 3 years, because this project will last for 3 years, so it will concluded in September 2020 and 22. So we have still a long way ahead, but I feel that the results of the first year, we are going in, let me say, in the right direction. And this is the architecture that we have prepared, and we have, let me say, created for our software SIMS framework. It is quite complex, but I feel that at the end of the session, after the different presentation from the research unit, this architecture will be more clear. But in any case, we do have collection. If we start on the lower left part of the architecture, we do have collection of real data coming from the real system, including big analytics and methodologies for big data analysis. We do have the different areas in terms of methodologies that I was mentioning before, and as well as we do have interaction with company informative system and the technological framework based on virtual augmented reality and simulation that I was talking before. If we would like to see a simplified version of this architecture where all the different research units are also highlighted, I would say that we do have, starting from the bottom part of this picture, we do have some research unit, like for instance Polytechnic of Bari and University of Palermo and University of Basilicata, working on the methodological aspect, including operator staging problem and cognitive problems, as well as ergonomic issue and cognitive and cooperative models. Then we collect data, and this part is related to University of Salerno, and in the end we are going to create the technological environment that will be created by University of Calabria, where we are going to verify and validate our model, with the aim in the end to apply our results to real manufacturing system. And indeed, we do have also different ongoing project case study with companies in order to to involve them from the beginning and during the development of our models, as well as in the final experimentations. So this is the Gantt of our project. As I mentioned before, we are now at month 14, so we are just after the first year of project. This was just a very brief introduction, because now we will go through the different research units and presentation to see what the different partners are currently doing. Obviously, if we are totally open for new collaboration. So if you want to join the project, even in terms of possible joint case study, because maybe you are working in similar areas, or you would like to carry out joint publication and so on, please feel free to contact us. Again, the consortium of this project is totally open to to interact with research unit, to carry out new case study, or to enlarge the scope of the project, as well as to do joint publication. Now, this was just an introduction. I will give now the floor to Polytechnic of Bari, that will start his presentation.
Okay, so I'm here. I'm going to share the screen. So can you see with the full screen mode? Okay. So to everybody, I'm Andrea Lucchese, and welcome to this special session on Smart Operators 4.0. This presentation will be focused on a set of new analytical models that consider the mental effort of operators in Industry 4.0 and also the aging phenomenon. So this is the framework that has been followed. So in Industry 4.0, both in production safety environments, these environments are characterized by both cognitive and motor tasks, and depending on the specific mental effort demanded to operators, they are subjected to more cognitive or more physical effort. So in this regard, the aim of the models developed is to evaluate the operator performance in terms of time-based measures and error probability-based measures. So in the Industry 4.0 context, operators are asked to process an increasing amount of information per unit time, coming to the necessity of developing new models that consider the increasing cognitive effort and physical effort of operators. Since in real life no pure cognitive or motor tasks can be observable, the following notation is adopted. So when I refer to cognitive task, it means an activity with high cognitive information content and low motor information content. Instead, for motor task, an activity with low cognitive information content, so high motor information content. So here are summarized the research goals. For production environment, the aim is to investigate and evaluate the mental effort in performing cognitive and motor tasks. Instead, for safety and maintenance fields, to evaluate the mental effort of operators in performing procedure-guided cognitive tasks. Finally, an analysis about the biometric signals as objective measurement for the mental effort has been made. So we start with the human cognitive efficiency. This can be analytical modeled with a ratio between the task efficiency and the cognitive load. So the cognitive load can be expressed with the product of the transmission rate or task load, so the amount of information that must be processed in 1 unit time, and K is a parameter that summarizes some characteristics of subjects, such as age or skill or experience, evaluated with the raw NASA task load index technique. Instead, the task efficiency is basically the ratio between the number of tasks correctly processed during the task and the total number of tasks that must be processed. So we now can evaluate the human cognitive efficiency, but we know from literature that when an operator performs certain activity, he or she is subjected to an effort, and the human capacity is limited during the information processing. So we must evaluate how much of the cognitive resources are required for that activity. So in this regard, we start from a model on the left. So in order not to be overloaded, the HOWL, which is the objective amount of information to be processed, must be lower than the mental workload threshold of the operator. So simply doing a ratio between these two terms, so we can see how much of the cognitive resources are required for that activity. So when the human cognitive capacity occupancy is greater than 1, of course, the operator is overloaded, as she or he cannot execute correctly all the tasks. So in this regard, we can also evaluate the time required to correctly process a single unit of information with the human information processing speed. So starting from the mental workload threshold of the operator, and using also the QE, which is basically the performance that is required for that task. So till now we have focused on cognitive tasks. Now we focus on motor tasks. So we started with the index of difficulty, ED of the fifth law, which is the amount of information to be processed to accomplish a reaching motor task of target width W and distance D from the starting point. So starting from this, we used it in a general trajectory, and we also apply it in 2 cases, so the tunnel traveling task and the circular traveling task. And we can see that both paths are constrained all along the trajectories. So starting from the index and the movement speed of the subject, we can evaluate the standard deviation of the endpoint position, so the accuracy of operators when they have to to perform tasks such as reaching task. So the further goal is to extend this model for trajectory that are needed in real work environments. So focusing on both cognitive and motor tasks, we can also evaluate the human performance time that has been modeled with time for the cognitive task and the movement time for the motor task. For the reaction time, so the amount of information to process has been evaluated with the Shannon entropy, and instead with the motor task, the amount of information to be processed has been evaluated with the index of difficulty. In particular, for both tasks, starting from available in literature, the information processing time, so the time needed by the operator to process one bit of information, has been modeled basing on the characteristics of subjects, such as sex and age. So the human performance time takes into consideration both the characteristics of subjects, such as sex and age, and the information, the amount of information that must be processed. Of course, this information processing time can be also expressed basing on the maximum oxygen consumption of the operators. So in this case, we consider such as the health state of the individuals. So changing and focusing on procedure-guided cognitive tasks, the concept described with the Shannon entropy can be also applied in case of maintenance or safety procedures in order to evaluate the complexity of the procedure and the mental effort of the operator. So the framework is the sequent. So first of all, start with tasks defined by maintenance or safety procedure, then convert this procedure into a graph, so with nodes that express the actions and errors, then evaluate all the factors that affect the complexity, applying the Shannon entropy to the graph representation, and finally evaluate the overall complexity of the task with a methodology called the Taxonomy measure. So there are some parameters that affect negatively the complexity, such as the task arrival rate or task uncertainty. So the task arrival rate expresses the number of tasks that an operator must perform simultaneously. Instead, the task uncertainty in the quality of information provided to the operator. Of course, for example, increasing task uncertainty decreases the quality of information provided. So we can see, focusing on the figure on the right, for task 1, that increasing the task uncertainty, the number of steps that the operator has to process and to perform increase, and so increasing also the complexity. In fact, we focused on the task uncertainty and applied this concept on a maintenance procedure for cleaning and lubrication of machine tools. So on the left, we can see a procedure, the standard configuration. On the right, instead, a new configuration where more information with higher quality have been provided to the operators at the starting phase of the task. So we can see that the path that the operators have to process decrease, and so decrease the decision-making process of the operator. So the number of paths that had to be analyzed, and so the overall complexity of that task. But there are also some parameters that can influence positively the complexity. So these are the Industry 4.0 technologies. In fact, these technologies can simplify the decision-making process of the operator. This decision-making process can be expressed with the decision ladder. So the simplification of the decision ladder can be reflected to the simplification of factors that are associated to the decision-making process. So to the simplification of its graph representation. And what are the conclusions? That operators are subjected to lower mental effort, and also that the operator can execute more complex tasks since he or she its subject is supported by the Industry 4.0 technologies. So about the operator, of course, as said before, the operator has a limited mental capacity, and the operator can process a limited amount of information per second. So this can express it with the information processing rate, EPR, modeled with the ratio between the TECOM, so the complexity of the task, and the TPT, the task performance time that is needed to the operator. It has been modeled with a parameter K that expresses the level of work experience. So focusing on the figure on the right, we can see that changing the K parameter, so the level of work experience, also changes the information processing rate for that operator. So I finally want to conclude with the analysis about the biometric signals as an evaluation for the mental effort. So we started from a test, the MBEC test, that is a cognitive test, summarized so the cognitive effort of the subject. So subjects see a sequence of letters on the screen, and when there is the target letter, the subject has to press the left shift. For the 0 back level, there is only one target letter. Instead, for 2 back level, there are more than one target letter, since the target letter is the letter that appeared 2 letters before. So in this case, the operator had to memorize more letters, and so increasing the mental memorizing that letters. So finally, we evaluated the difficulty in with two main measurements. The first is an objective measurement, so basing on the biometric signals, such as the heart rate variability. And the other measurement is the NASA task load index technique, which is a subjective measurement that reflects the difficulty perceived by the operators. So results stated that both measurements are reliable, and they reflect the difficulty in performing a task, in this case for this test, so paving the way to evaluate to the validation of these measurements on real work environments. So before to conclude, I highlight this special issue about these topics, human factors in the digital society, which deadline is 28 February 2021. You can see so the QR code and the link, and this special issue is guest edited by Professors Francesco Facchini, Salvatore Giesi, and Carlotta Mummalo. So you can see here summarize some indices and some information about the journal, so which is Applied Sciences. So with this slide, I've concluded my presentation, and thank you for your kind attention.
Thank you. Thank you, Andrea, for your presentation. We leave the question time to the end of the session. Now we have seen how the cognitive load problems, Andrea has explained how within this project we are taking into account the cognitive load problem for our operators. We will move now to the second presentation that will be given by University of Salento. I feel Giulio will now share the screen.
One moment.
Yeah.
Okay. I have just a problem. Okay. You could see my screen?
Yes, please.
Okay. Hi everyone, it's a pleasure to participate in this special session. I'm Giulia Newsday, I'm an engineer, I'm a PhD student from University of Salento. The director of our research group is Professor Maria Grazia Agnoni. During this presentation, I will show the activities of our research group and to this research project. In particular, we have, in particular, a literature review on current application of digital twin in smart manufacturing field as carried out. Then we have conducted an analysis of applicative case study supporting industrial safety. We have developed a framework in order to collect knowledge from applicative fields and in order to collect information from adopted technologies, both for data acquisition and both for simulation. Then a proposal of a classification framework considering the analyzed case study as carried out, that this classification framework could be used for our digital twin system. Related to the research project, we have published 2 conference papers and a journal paper. Digital twin, according definitions in literature, is a model in which physical world and digital world communicate between there are 2 main definitions. The first one by Grips and the second one by NASA. The second one is the most used definition in to explain about digital twin. This is a graphical a schema of data of a digital twin, and in particular information in particular physical environment and virtual environment communicate. There is a data processing that data could be processed by statistical technique or simulation modeling, or in a more advanced system by artificial intelligence. We have, by using BEHAVIOUR software, a bibliometric analysis has been performed. We have extract from Scopus some paper contained by using the keywords digital and twin. So we in the figure we show the 7 correlation cluster extracted by BEHAVIOUR software. Then a complex analysis was carried out, and using digital and twin and safety keywords. So we can observe that in the 2018 and 2019 there is an exponential growth of number of articles published in literature. The available paper have been classified according to field of application. We can observe the P chart, and in particular the most number, the main field in which paper are the main field of application is manufacturing. The results of the analysis confirm that digital twin for safety purposes is used in mainly in the manufacturing and robotics fields. There are three main purposes for which a digital twin is used in the safety field: predictive analysis, real-time monitoring, and training. The main purpose for which digital twin is used in the safety field is certainly predictive, because it allows to cut development cost of real models of product and or processes. In this slide, we show a proposal of digital twin framework in safety field. The classification was carried out according the acquisition by classifying the acquisition tools and data processing tools. So we obtain this the model shown in the figure. The future activities consist in the classification, in the elaboration of a classification framework, define use case, define some use case, define acquisition data strategy. We started a collaboration with Bosch plant in Bari, and we have defined we will define a scientific committee to with end user and institutional partners.
Thank you, Giulio. Here in this presentation, we have seen how we are facing the problem of collecting data. So let's move to the next presentation that will be given by Professor Aiello from University of Palermo, that will focus on another aspect of the SOFOR-SIM project. Giuseppe?
Yes, I'm here. Okay, let me share my screen. Okay, do you see the screen?
Yes, perfectly.
Yes, so I just connect to what you were saying before concerning the fact that the smart operator has a lot of features that can be enhanced by new technologies, typical technologies and key enabling technologies of Industry 4.0. And in this case, we are speaking about the context of operators' safety and, okay, let's say ergonomics and safety. In particular, what we've developed so far is a brand new methodology to link to peculiar aspects of operators' safety in the context of smart manufacturing system. And in particular, what we want to do is to link the aspects related to activity recognition with the aspects related to physical risks. And in this case, we are mainly speaking of safety risk, health risks related to vibrations, which is the source, the origin, the cause of many work-related, occupational-related diseases. Okay, so this is the topic we are addressing, and This is a very brief and easy to catch description of our current state, our current situation. Okay, so far we completed the literature review and also we set up a new methodology, and basically that's where we are right now. Unfortunately, let's say our work plan had in cooperation with some companies and enterprises at an experimental part. Unfortunately, due to this COVID issue, it has not been really easy to make the experiments because of two main reasons, basically. The first one is that our laboratories are not working on full, let's say, on full scope. So many technicians are not coming to work and so on. So this has hampered the development activities, the activities related to the development of the wearable system for measuring vibrations. And the other issue is that companies were not available in let's say supporting us with their workers. We wanted to make some experiments in some shipyards and other manufacturing contexts, but unfortunately, due to the restrictions related to the COVID, they also have limited, let's say, activities and a few people working and so on. So therefore, the experimental part is being, it is a little, let's say, hard to catch up with these activities, with these experimental activities. So far, in any case, we developed a methodology that is still under development, and we tested the results against some data sets we gathered, since it is actually almost 10 years we are working with this topic. So therefore we had some old data, let's say, from other experiments, and we used this data from the lab that we have in order to test this new methodology. But of course, what we would like to do is to update the data set and use more, let's say, within this project, a substantial technological update was supposed to be done on the device, so that would have given better results in terms of available data sets. So far, again, we just test our methodology against old data that we used to have already collected in our lab. So this is basically the state, the place where we are now. So these arrows basically show where the project is gone so far. Okay, so very rapidly, the agenda so far, we are okay. As I said before, we defined the methodology, we established the methodology to deal with activity recognition and risk exposure, based on the analysis of the vibration data streams that have been gathered physically through on the operator, I mean, through a wearable device, and based on these data sets. Okay, we perform data acquisition and preprocessing, meaning, for example, that some data sets, when you're working with the accelerometers at high sampling rate, it is quite normal that that you have some false readings or some missing readings, and in that case, so you have to do some preprocessing in order to have, let's say, well-defined data sets, so that you can go further with the feature extraction. So when let's say the activity classification is based on a machine learning approach, and the machine learning classifier is fed with some features extract from the data streams. So the activity chain is first the acquisition, then preprocessing. After that, we have feature extraction, and then these features, they are fed to this machine learning classifier, and at the end, through this methodology, we are able to classify the activities that the operator has done during the monitoring time, and associate a risk factor to each one of these activity. So therefore, we can reconstruct the story of the time series of the activities done, and the corresponding risk exposure of the worker, which can also be exploited. Such information can also be exploited in order to, for example, predictive considerations about the task assignments and so on. So it is, let's say, mapping the activities with the corresponding risk. Not only is useful to prevent dangerous situations for the operator, but also it can be exploited, such information can be exploited for better task assignment procedures, for improving the task assignment procedure, and also the schedule, improving the schedules of the activities and so on. So basically, okay, let's have a look at this. This is basically the methodology that we have developed so far. So what I was saying, the actual result we are looking for is the mapping of the activities done plus the risk exposure of the worker. And this is the final result. So we established this methodology, which is based, okay, basically here we have the operator working with some kind of tool which is generating some vibration. In this case, we typically refer to rotary machines that usually they produce vibrations that cause damage to the hand-arm system. So there is this, there's a, let's say, literature and the scientific support which says that hand-arm vibrations, they are related to some occupational diseases, and in order to prevent the worker to let's say physical damages, then these vibrations should be monitored, and maximum allowable dose is when a maximum allowable dose is achieved, then this is a threshold, and the operator should stop working and maybe rest, and then again next day, and so on. So this information is important in optimizing also the task schedule, not only for preventing safety and health risks, but also for improving the task scheduling processes. So basically here we have the operators working with this tool, and this is something we simulated in the lab so far, but again, it was supposed to be an experimental activity, a real experimental activity. We have companies cooperating on that, and they are interested, and they are willing of doing this research. But clearly, due to this coronavirus issues, this has not been possible so far. So this is an operator which has some sensors on this verse, and also a wearable device. And by means of this wearable device, the vibration signals on both hands on the 3-axis, so this is 3-axial acceleration signals, they can be gathered. Consider we are speaking of polling frequency of about 1.6 kilohertz, which is quite a lot. So not only the accelerometers, the sensors, they must be of a state-of-the-art technology, but also the wearable device should have enough computational capabilities in order to handle this data stream. So these data streams, they are segmented into time windows. In our case, it's 40 seconds, which is quite a lot. Increasing the length of the time windows. This increases the computational effort. So therefore, the segmentation process should be optimized according to the computational capabilities of the device. So from each one of these segments, when the entire signal is subdivided into chunks, into segments of 40 seconds, then each segment is analyzed and the feature extraction part of the methodology takes place. And actually we have two kinds of features. When you analyze vibration, they can be features extracted in the time domain or in the frequency domain. Actually, we use the time domain features for feeding the classifier, the machine learning classifier, and performing the activity recognition task. While on the contrary, also the fast Fourier transform has been calculated, and the features extracted in time domain, they are used to this is actually prescribed by the guidelines, health and safety guidelines, and so they are used to evaluate, to assess the corresponding risk. Then these two procedures, they again match together so that we can actually have a map of the activities performed and the corresponding risk exposure of the worker. This is actually done in semi-real time, and by means of this of the decentralized architecture we set up, actually it is possible to simultaneously monitor the risks of several workers. So we imagine a smart factory context where several workers are working there together, and by means of this wearable device, and clearly, okay, this wearable device basically makes all this process, and the results, they are, let's say, shared, they are uploaded into a shared ledger. So actually, for the managers, they could actually be able to monitor the situation of several workers simultaneously. So basically, what we have here on this right side of the slide is what I discussed. This is just with a little more detail. So we have normalization, feature selection, and feature extraction. And actually, what we want to do is to test the performance of several classifiers, several machine learning classifiers. But so far, we just implemented one, which is the KNN classifier that you see here. Okay. So this is just to show what this is real data. So this is, let's say, theoretical methodology, and this is the application to real data. And we have the three data streams, the different segments, and they are all put to, let's say, they all belong to the same vibration system of, let's say, in this case, the left hand and the right hand, and so they are combined together in order to extract the features. So this is the time domain, and this is the frequency domain. So features are extracted from this pre-processing step. Okay, basically, this is what I was saying before. Here we have time domain features and frequency domain features. Time domain features, they are used for activity recognition, while so from the same data trunk, from the same segment of data, clearly they are fused together because these are actually three different data streams, because the accelerometer is a 3-axis accelerometer and it generates 3 separate data streams, and they are fused together into let's say a single feature extraction procedure, and because of course for example for the risk assessment and also for the activity recognition, it is clearly important to let's say fuse the information from different sensors, fuse the information together. Clearly, for example, the risk is clearly a result of the vibration in all the three axes clearly. So these three data streams, they are combined together, they are cut into segments, then recombined together, then the features are extracted, and the time domain features, they are used for activity recognition, while the frequency domain features, they are exploited in order to perform the risk assessment. Then these features, speaking about the time features, time domain features, they are fed into a machine learning classifier. So here you can see we have the general taxonomy of the classifiers, so the machine learning classifiers. Actually, we use the KNN, the key nearest neighbors, and but the idea is to let's say extend the methodology by implementing different classifiers in order to improve the performance, which, as you will see, is already pretty good in any case. Okay, so basically what we did so far, we select the classifier, in this case the KNN classifier, and this is what we employed. Basically the feature, here you have in this table the time features domain employed for classifying the activities, and in the lab we simulated different possible activities typically happening in some manufacturing contexts, and with different tools, and in order to simplify the approach, so far they have been classified, all these activities that have been simulated in the lab, they have been classified into two classes, which is heavy duty and light duty activities, and this is reference idea of the average vibration levels. So as you can see, light duty activities, they have vibration levels, vibration doses around 5 and 10, while for instance heavy duty, they have more than 15. Okay, so given this classification, the features extracted by each segment, all the segments have been, this is a supervised learning method. So all the segments, all the data trunks, they have been classified, meaning that it has been established if they are related, if they were related to heavy duty or light duty activity. So this is the procedure employed for the KNN classifier for recognizing the activities, while this is the risk assessment procedure, which again is related to the vibration values and to the this methodology is actually suggested by the ISO guidelines. So
Giuseppe, sorry to interrupt you. 1 minute, otherwise we go out of time for the other presentation.
I'm done.
Okay, thanks.
So this is the results, and okay, as you can see, we made some different instances because all the segments, they've been randomized. So therefore we have several runs by combining differently, and here you can see the KPI we use to measure the accuracy of the classification. Each set of data analyzed, they had 500 segments, and 100 of, let's say 400 of them were used for as training set, while 100 segments were used as a validation set. So this is the table of the results, and this is actually what you can see. And basically this is the false negatives, the false positives, so the errors. So the total classification errors, as you can see, the classifier with k equal to 3 has less errors than the others, and it actually shows also here because it has a very high classification accuracy. So also we selected the most effective value for K, which is generally established via trial and error. And this is the final result. As you can see, we have a time span of 3 hours more or less, and the system was able to classify the different activities into low duty and high duty. Also here we have no activity situations. The corresponding risk exposure. So basically this is the final result, which again is the map of the activities performed and the corresponding risk exposure. This could be seen in real time for many workers simultaneously. So therefore, this information can be shared on a shared ledger again, so that also managers, they can understand, they can have under control the situation of health risks related to vibration in the smart factory. So that's it. And I'm sorry, I mean, this presentation was done quite in a hurry, so you don't see any fancy stuff.
Don't worry, Giuseppe, and thanks a lot for your nice and interesting presentation. We have seen currently two major aspects of the software sim project, one related to risks for operators, in particular vibration, and the other one for cognitive loads. And both of them, we have noted that they need data to be collected from the manufacturing system. This was the presentation that was given by University of Salento and Giulio. Now we move to a different aspect, and we will go with University of Basilicata, that is going to introduce another aspect that is quite important for the smart operator. Fabio, the floor is yours.
Thank you, Francesco. Are you able to see my screen? I think
yes.
So. Okay, I will try to put in presentation. Just to make a little reminder, because my group of research is composed by 3 researchers and a PhD students. The group of research is a little bit heterogeneous about competencies. There is some people inside the group with competencies on industrial, and some other people inside the group with competencies on material and robotics. In particular, this group of research is mainly, according to the project, focused on the interaction between human and machine. The main activity of research that we performed started with a state-of-art analysis. It was conducted in a kind of a systematic approach in order to understand if there is some main concepts when we are studying collaborative system. In particular, we focused on journal papers. Okay, try to make a kind of map which were the main concepts or the main elements that we need to discuss if we want to, in some cases, manage the relation between human and robot. Okay, according to the main state-of-art analysis, we performed a kind of connection map between what we related to the sustainable risk factor. In particular, we noted that the majority of the state-of-art stated that if you are trying to study or you are trying to optimize the relation between human and robot, you need to focus on the aspect of human as it's the central element of the optimization, but you need also to focus on some aspect related with the environment, some aspect related with the process, and the organization of the work cell as well. The main state-of-art was then clusterized according with our this state-of-art was performed in the first year of the project that started in 2019, but in the second part of the project we decided to focus on an aspect of the state-of-art analysis that is related to the cognitive effect. In particular, we developed another clusterization, okay, in order to find if the literature review is talking about some relevant study to measure the cognitive aspect. We related this cognitive, this aspect with the map that we previously implemented, and we tried during this year to implement something in the aspect of cognitive. Our approach to the problem was about functional behavior structure. That means that if we are studying the cognitive aspect inside the system, we need at the beginning to focus on the behavior. In particular, the behavior need to be interpreted according to different levels. The first level is the level of perception. The second level is the level of comprehension. The third level is the level of prediction. Okay, perception, comprehension, and prediction can define, in our perspective, a kind of design test or design of the system. Okay, that can be simulated using some tools that we can find in literature. Can be simulated according to traditional simulation model like discrete level simulation, but maybe they can also simulate it according to some other kind of simulation approach, would be merely related to the algebra and the modeling, or maybe to the system dynamics perspective. The idea in this way is starting from the perception of the environment you need to develop. We can define the design that constitute the structure of the environment. The environment change the comprehension of the system, and eventually we can test some features inside the system. According to this, the approach of the group of research started with the idea that we can eventually use some tools like graphical user interface or virtual tools or augmented reality tools or mock-up in order to capture the human comprehension inside the system. The tools can define the human action inside the model. Okay, the model can be set according to some state interaction between the agents, and eventually it is governed by the behavior. Our cognitive approach to the problem was generally related to this kind of map. We performed some tests inside this perception. The test was conducted using an element that is the ACE movement. In particular, we modeled the ACE duration inside different tasks. We try to investigate different complexity tasks using a simple task like the resolution of a cubic cube, and we made according to the visual representation of the ACE movement, and according to some other external tool like the for capturing the heartbeat, we make the correlation between ACE dilation and heartbeat. We find it that according to our preliminary test, there is just a connection between ACE movement and age, a connection between ACE dilation and age, and eventually there is also a connection between the type or the category of age. In particular, in our formulation, we used some similar to a complexity-based behavior to the concept of entropy, using an exponential negative function. But we found that the young worker has a human factor that is that has a larger amount. On the counterpart, the old worker has a kind of human factor, human factor that is more near a medium value, more near a medium value. The idea here is just.
Sorry, Fabio, maybe there is someone with the microphone switched on.
Okay, I don't know if the microphone is
check.
well. Okay,
go.
Okay, I can go. To this perspection, we try to define a kind of framework in which the human factor is inside. The framework is the framework consider the operator consider the human operator inside the block. The operator is in connection with the entities inside the systems with the human-machine interfaces. In our simulation perspective, there are some entities with which we want to cooperate. The first entity is obviously the robot, but there are also some other entities, like for example machine, logistic systems, product, and eventually the equipment. The idea is in this system to work inside the physical system in order to plan some experiments relating to the environment and eventually to check if there are connections with the known features. This is just another vision of our simulation environment, which we try to connect the simulation field with different levels from an informatical point of view to the optimization phase, like a kind of what-if scenarios that we can construct inside the system. And we interpreted the perspective of the environment according to a decision map clusterized according to technical informatics and physical behavior. Based on our main perspective of the model, we decided to focus on a case test. The case test is related with, is a kind of test in which we try to model the collaboration between human and robot. We used the collaborative task with an operator that needs to collaborate with the Cooper robot and the Najibu systems. It was arranged according to an automotive field, okay, and we try to simulate this scenario based on rule, simulated rule. We used a particular logic behavior in order to check which were the main relevant rule inside the systems. Okay, this is the perspective of the agent or the connection between agents. We work in the field of simulation. Okay, these are the states that describe the element inside the system, like the AGV picture, the AGV that is moving inside behavior. The work is clusterized according to states. Here there is just a kind of simulation scenario in which there are different AGV which are parting. There is a kitting area. The AGV need to move according to rule from his starting point to the kitting area, need to move in a station when they are performed based on the cooperation between human and the worker and performing some manual operation. And we testing some rule in order to find which were relevant to the fitness, to the outcome of the environment. Here there is a picture of the states that we simulated. This was presented into a conference. Each states of the element in the system was simulated according to system dynamic perspective with a lot of parameter, a lot of variable and a lot of function. Parameter was related to the behavior and the function was checked, was gained by the literature. Review, okay, and we perform a simulation test with different scenarios. Okay, currently our main intent of research is to include in the project, okay, another case study. That is the case study that we proposed, started from the beginning of the project, is about a factory, the Pinto Techno series. The case study is similar to what we already tested. The Pinto Techno is a factory working in the field of manifold. The manifold are product of different material like steel or titanium, and with different features, different weight and different size. They are generally realized by CNC machine that could be fitted by automatic various systems. The intent of the Pinto Technique is the case study which we are proposing inside the system is to define some optimization rule in the logistics, in the internal logistics, because the product after the CNC machine need to be manually worked. They are currently trying to investigate about, they are trying to include a shell, an automatic shell in which should be a collaborator between you and a robot. They are thinking to implement inside the system an AGV system with a motor inside, and the AGV system with a kit inside, and a manipulator need to move the manifold product in order to give access to the task of the operator. So the idea is to work in the field of collaborative system with a collaborative shell in which there are moving entities with a manipulator on board, and there is a robot and entity that is moving the product inside. Just to conclude this presentation, it's just a short idea of what we did. There is currently a session proposal to a conference, the conference, which the deadline is the end of this month. The section is about smart interaction for operator-friendly robotics. If you would like to participate, there is still time. And another suggestion is, if you are interested in the topic of the conference, there is a special issue in Journal of Simulation and Process Modeling, in which I am a guest editor, and the deadline is at the end of January. If you would like to participate at the topics, your proposal will be welcome. Okay. I think I was really fast. Sorry.
Thank you, Fabio. Fabio has introduced an additional aspect for our smart operator, the collaboration with other entities within the shop floor. We move now to University of Salerno, that is going to present the last methodological aspect related to the SO4SIM project, before seeing in the end the technological framework to host all the methodological contribution that we have described until now. Valentina, the floor is yours. We cannot hear you, I feel. Okay, can you...
Chiedo scusa, ho perso un passaggio, ma qualcuno lo sapeva, ero praticamente in presentazione su un altro...
Fabio, can you shut down? Can you close your microphone, Fabio, please? Okay. Valentina? We cannot hear you, Valentina. You have a problem with the microphone, I feel.
Now, can you hear me?
Yes, perfect.
Okay, thank you. And the presentation?
Yes, you can go ahead. We can see the screen.
Okay, now it's okay?
Yeah, perfectly.
Okay. Good afternoon to everyone. I'm Valentina Di Pasquale, a research fellow from University of Salerno. I bring you also the greetings from Professor Miranda, who unfortunately today is unable to join to the session. This afternoon, as a member of the research unit of University of Salerno, I'd like to provide an overview of our role in this project and to present the main work activities carried out by our research unit. As said before and showed before by Francesco, this is the initial proposal of our project, and in particular the University of Salerno, the research unit, is involved in the analysis of performance of smart operator with particular attention on the aging phenomenon. But why this choice and why for us this aspect is so important? It's important, and in this sense it is essential to underline that one of the main challenges that industries are facing in this year, only one moment, okay. One of the main challenges that industry are facing in recent years is the aging issue. Nowadays, population aging is recognized as a global trend, as for example we can see in this slide when we can see the percentage of older people among the European population, and this trend is transforming the global demographic landscape, having a significant impact on various dimensions of our our society, including the workforce age profile. In this figure, we can see, for example, a trend over time of two different groups of workers over the time. For this reason, great attention is given nowadays to age in working contexts where older workers are growing, raising, of course, several questions about the value of older workers, because they are, of course, the most skilled and experienced employee, but they are may also be more vulnerable, less reliable than their younger co-workers. Probably is also our daily experience. We know that with aging and age impact both on physical, cognitive and perceptual abilities, leading an important effect on working performance. This consideration therefore underline as it is necessary, in our opinion, to evaluate how aging can influence the interaction between workers and enabling technology, and so Industry 4.0 paradigm, and so what are the performance of smart operator if we consider different age, group of age. So focusing on the project, our research unit is leading the work plan related to aging workforce performance with the aim of developing new model for assessing the performance of older workers as function of different factors that are the experience, the learning and forgetting processes, the different type of working activity, but also all the environmental and organizational features that characterize the Industry 4.0 context. This work plan is divided in 4 tasks related to the definition and evaluation of the effect of age on workers' performance, the definition of psychophysical recovery of older workers due to the work break during a shift, the analysis of learning and forgetting curves, and finally the definition of all the contextual and individual factors that can impact on the performance of aged workers. As said before by Francesco, we have just completed the activity planned for the first year, and in particular, in our case, related to task 3.1 and 3.2, that now I'm going to describe in detail. Moving on the first task, so the task related to the definition and evaluation of the effect of age, the purpose of this first task is the identification of all the effect of all the impacts of age on worker performance. To achieve this purpose, we conducted a systematic literature review and in order to define a theoretical framework for assessing all the factors that impact of age on worker performance, considering so the different kind of errors, injury, accident, and so on. We identified in this task 3 different steps. In this moment, to date, we concluded the analysis of age-related human capabilities, the impact of age on human performance, and we are working on the identification of smart operator capabilities. In particular, in the first step, we conducted a literature review on age-related human performance in order to identify and in particular collect all the data about the cognitive, perceptual, physiological capability that are age. Only for for your information, and we can see here some of the results related to the a specific category. So in this case, the physiological category, human factor category, we define all the abilities that are affected by age. The same for the cognitive capability and for the perceptual. And this step allowed us to understand the several effects of age on human ability as a preliminary and essential analysis for the next step. In fact, in the second step, we conducted a specific systematic literature review using the keywords that we can see in this table, with the aim of understand the relationship between age and human system error in manufacturing context, considering also the important role of experience that in some cases can balance the negative impact of age, if we consider older workers that are also the most experienced workers. We also investigate the human factor capability that are influenced by age and connected to human error. We tried to identify the possible human error taxonomy that considered, that evaluate the effect of age on operators' performance, and finally we tried to understand the impact of this age-related error on manufacturing system and on manufacturing operation. Starting from a huge set of paper, finally we selected 26 papers, and moving on the the first result of this review, we built a structured framework of all our results from considering the data extracted from the selected paper, trying to identify all the main key elements that consider the relationship between age and human performance in particular in a manufacturing system. Starting from the evaluating in detail all the results that we obtained by the systematic literature review, we were able to develop a theoretical framework on age and human performance. In this framework, you can see as continuous line all the information that we extracted from the literature, so they represent the current level of knowledge that we find in literature, whereas the dashed line are all the research gap and the future research opportunities that we identify in the literature. In particular, we found and we noted a lack of analysis of the use of enabling technology for improving human performance, above all if we consider older workers. And now we are working on this, on the last step of the task 3.1, in order to identify the different kind of smart operator, the feature of the main smart technology, enabling technology that can help and support older workers in order to improve their performance. Moving on the next step. The second step of our work is related to the evaluation of all the psychophysical effect of continued work on the performance, also in this case, of older workers. Through a systematic analysis of the literature, our main purpose is the definition and identification of the optimal scheduling of work breaks according to the different age of the operator. Also in this case, we divided the task in three different steps. We completed to date the first step, and we are working on the second step related to the break scheduling for older workers. In particular, considering the aging and psychophysical recovery, we, as first result, we consider, we studied work recovery, and we found that this is a function of physical activities, recovery speed, the cognitive and mental effort, the age, of course, and the gender, and we define a specific matrix, specific table in which we can see the optimal break time as function of the different factors that we have considered for this activity. So after completing the activity, so the first year, we are now also starting on the other two tasks. But for this, we don't have results, but we have structured our work. In particular, the task 3.3 is related to learning and forgetting curves for, also in this case, for older workers, with the aim of identify the learning and forgetting coefficient according to the different age group and type of work activity. The last one, a task for our research unit is in a certain sense the global aim of our research work, so the definition of all the contextual individual factors that impact on the performance of agile workforce, because the main purpose is the identification of all these factors in order to model new human performance model and new human KPI indicators. Summarizing our work, the work of our research unit, this is only a preliminary structure of the work, considering for all the key elements of each task. So we see in particular the steps related to the first task and the second one, but we are now working on the other two tasks and on the single step that we identify, in order, of course, to obtain as main result the human performance model in the specific context of Industry 4.0, taking into account also the important aging problem. Thank you for the attention.
Thank you, Valentina. Now, so we have seen all the methodological aspect of the software sim project. We started with data collection, then we moved to cognitive loads. We have talked about aging problems. We have talked about collaborative action within the shop floor, about risk. So all these aspects in some way are quite important for the implementation of the smart operators. We move now to the last presentation. We know that we are out of time. I mean, we are almost close to the end of the session, but I feel it's important to go ahead with the last presentation to see how all these different aspects can be finally combined in a technological demonstrator and framework to implement the final solution of this project. So I leave the floor to Antonio Padovano, that is going to make the last presentation of this session.
So can you hear me? Can you see the screen?
Yes.
Yes.
Okay. So thank you, Francesco, for the introduction. I know that we have a few minutes, but I will give you just an overview of which is the role of the University of Calabria in this project, in the software sim project, and also show you some of the initial prototypes that we are currently using as part of the project. So just to give you an understanding of which are the things in this project, basically UNICAL will develop simulation environments that will serve as a showcase of the potentials of the overall system, as a sort of integration of all the research outcomes that the other colleagues from other research units have just discussed. UNICAL will also provide some front-end applications based on virtual and augmented reality, as well as interfaces for wearable technologies available at the operator, and in order to develop and enhance man-machine interactions at the workplace. And also, we will collect operator's health data gathered from wearable devices. So in order to collect data from operators in the shop floor and understand if there is any ergonomic issue, work-related stress, and so on. Just to give you a background, as also has been discussed previously, the operator 4.0, also called smart operator, is going is undergoing a revolution nowadays. We consider not just physical interactions, but also cognitive interactions with machines and with technology. And even though people, have started to fear this transformation from human work to robotic work, we can actually analyze and try to support human workers at the workplace. How? So this is a picture basically telling us that today we are living in the era of social smart factory, where everything in the plant, everything in the factory, manufacturing all the resources from products, workers, work orders, robots, resources and environments are today equipped with intelligence and data. So basically, all of them are able to interact to each other and exchange data and basically provide some intuitive interfaces in order to achieve the agile manufacturing system. We have started our understanding of the smart operator literature by giving an outlook at the previous work, and we analyzed Scopus database in last February, and we saw that there were 28 eligible studies that we have classified according to their type and contribution. Basically, the main results of this analysis is that while there are a lot of conceptual work on this topic, there is also very few analysis and understanding of how we can really support in practice the operators by using practical technologies, practical tools. So this is why we are trying to shift a little bit the focus in this project of the smart operator towards a cognitive, sensorial and physical interaction capabilities, which are augmented by the use of Industry 4.0 technologies. And in this picture, I'm not going into the detail, but here are represented more or less all the technologies that operators human workers can use in the shop floor, in the factory. I'm also giving you some references to our publications, to our papers, so that if you want to know more, you can read the full paper. What is interesting is that why, from a previous analysis, is that we carried out also during the preliminary phases of this project, is that while a lot of respondents, a lot of people in companies actually know the technologies, they say, as you can see from the graph above, they say that the technology is considered very critical at the executive level, but there is a very small percentage of enterprises or respondents that have actually adopted the technology. And as you can see from this three-map chart of the perceived beneficial impact of operator 4.0 enabling technologies, you can see that the major impact is on these red areas, which means they are based on which means that operator 4.0 enabling technologies can actually support the operator more from a cognitive point of view rather than physical. So just wanted to move to the main part. What is important is that the unique contribution in this project is that we are developing and designing the environments where the contributions from the different partners are coming and will be integrated to each other. In particular, as you can see, data from the cyber-physical systems will be integrated and will be made available in the digital twin, so that this kind of data in the digital twin can be used in a very intuitive way by using several interfaces, such as the one that you can see below, such as mobile phones or vocal interaction like Siri or Alexa. So this kind of technology is also getting into the industrial production. As you can see, simulation-based augmented reality and virtual reality environments will be used to test the results and models that will be developed during the project. So we are working with augmented reality solutions for the smart operator, virtual reality solutions for training, for decision making and so on, but also wearable solutions. Applications are manifold. We can apply these environments and these prototypes in several domains, from maintenance and prognostic and health management, troubleshooting, personnel training, and safety and security. What is important is that we are developing this in the concept of a digital twin, which means we receive data from the cyber physical system and we analyze this data within the digital twin so that we can give an immediate feedback to the operator, which is both in the shop floor, but also maybe in a control room. So these are just some future research of our research unit. So we will develop, we are developing technological tools and environments enabling multiple analysis. Just to name a few, evaluation of the cognitive load, so in collaboration, for example, with Politecnico di Bari, test predictive and prescriptive maintenance, building occupational health and safety 4.0, carrying out experiments for ergonomics, as Professor Aiello was mentioning, as well as understanding the usability maybe of new technologies on aged workers. Aging, as Valentina was mentioning, is extremely important. So these kind of environments will be the perfect test bed for everything we have discussed so far. I'm just putting here some references that serves more or less as the basis for our work. And also I would like to invite you to submit a paper to our open invited track at INCOM 2021, which is on the concept of Operator 4.0 smart interfaces for human automation symbiosis, will be held in Budapest in Hungary. And the deadline is very, very close, November 30th. You have to use this code for the submission, but definitely this is a very nice outlet, and also to continue the discussion on this topic. Thank you very much for your attention, and if there are any questions.
Thank you. I think we are out of time because it is already 5:35, but if there are questions, please feel free to raise your hand and you can ask questions about the different presentation that you have listened during the session. So if there are no questions, I would like just to invite you to consider the opportunity to join our research activities in this area. As Antonio Padovano was mentioning, and even Fabio Fruggero, we have different tracks in conferences as well as journal special issue that we are running on this topic. So there is space, and even in some way in the next edition of the ISM conference in 2021, there will be space for these topics and for joint research activities. So feel free to contact us. And if there are no questions, I thank you all the speaker and all the attendees of this session, and I feel that the session is over now. Thanks a lot.
Thank you so much. Bye.
Thank you,
Professor.
Thank you.